I now call to order the Society's 2,377th meeting in the 146th year since its founding in 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, the oldest scientific society of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Lindstrom. We will begin with a few announcements, followed by a reading of the minutes of the 2,376th meeting and a recounting of John Tyndall's visit at the 36th meeting on December 11th, 1872. We will then turn to this evening's lecture, followed by a question and answer period. Thereafter, I will present a small thank you gift to our speaker, make a few closing announcements, and adjourn the meeting to the social hour. Please join me in thanking the sponsors of the Fall 2016 and Spring 2017 lecture series, the Policy Studies Organization, in cooperation with the American Public University, and a generous anonymous donor. I'm pleased to announce that tonight's speaker, Lindstrom, has been elected to membership in the Society. And please join me in welcoming him. Preston Thomas, our recording secretary, will now read the minutes of the previous meeting's lecture on biological collections, which was given by Reed Beeman of the National Science Foundation.
At the Cosmos Club in Washington, D.C. on March 24th, 2017, President Larry Milstein called the 2,376th meeting of the Society to order at 8:11 p.m. He announced the order of business and welcomed new members. President Milstein reported on a presentation by Society members Alan Stern and Kirby Runyon to the International Astronomical Union proposing a revision to the definition of the term planet. Recording Secretary Preston Thomas presented a report to the Society on an ascent of Mount Kilimanjaro and observations regarding the data collected on the acclimatization of the climbers. The minutes of the previous meeting were read and approved. President Milstein then introduced the speaker for the evening, Reed Beeman, a program director of the Division of Biological Infrastructure at the Directorate for Biological Sciences of the National Science Foundation. His lecture was titled Biological Collections, From Dark Data to a Global, Accessible Digital Resource Documenting Life on Earth. Dr. Beeman began by explaining that biological collections are often misperceived as akin to stamp collections. In practice, however, biological collections, both preserved and live, provide an empirical basis for research as well as an invaluable historical record that can be studied years or decades in the future to further our understanding of the relationships between species. Preserving these treasure troves and making their hidden insights available to a wide audience is a critical project for the scientific community. Dr. Beeman explained that the project of describing nature goes back to the Systema Naturae written by Carl Linnaeus in 1735. Given the expense, uncertainty, and danger, Dr. Beeman characterized the expeditions of James Cook, Charles Darwin, Alfred Russel Wallace, and Edoardo Beccari as the moonshots of the 18th and 19th century. Current biological collections and their projects go well beyond the mere acquisition and classification that characterized the 18th and 19th century expeditions. Today, a major focus of collections is not exploring new lands, but racing to obtain samples and indigenous knowledge from areas that are threatened by habitat destruction or other permanent changes. Dr. Beeman explained that we may not be able to go back to some of these places, and among other purposes, biological collections provide an irreplaceable window into the past. Dr. Beeman explained that a sample in biological collection consists of a specimen together with its metadata, a scientific name, where it was collected, when, and by whom. If a specimen does not have that information, it is not of scientific value. Specimens are no longer stored in formalin, but in ethanol, which is generally safer, but is still flammable. Importantly, DNA can still be sequenced from specimens preserved in ethanol, meaning that the plunging cost of genetic sequencing can be leveraged to retroactively investigate samples collected decades or sometimes centuries ago. Dr. Beeman explained that in addition to preserved samples, slide collections, fossils, and skeletons, living and cryopreserved stocks such as algae, microbes, fungi, and rodents are a key part of modern biological collections. Through National Foundation Science support, samples of these live stocks can be ordered on a cost recovery basis, which makes them very available for research, promoting standardization. Dr. Beeman highlighted one such animal, a cute brown deer mouse, Paramiscus maniculatus, which is emerging as a potential supplemental model organism to the familiar white mouse, Mus musculus. Other living stocks supported by NSF include the Lemur Center, which facilitates cognitive, perceptual, and behavioral experimentation. Dr. Beeman emphasized that we may store collections for decades without knowing their usefulness, but if we do not store them, then we will never know. The advent of CRISPR-Cas9 demonstrates the importance of maintaining reliable, well-curated, and documented stock. The initial paper exploring the topic was published in the 1970s, and nearly 50 years later, consistent living stocks were available to further that research. Dr. Beeman concluded that if we resurrect the woolly mammoth, it will be because we took the time and effort to grow, curate, and analyze our precious biological treasure troves. After the conclusion of the talk, President Milstein invited questions from the audience. One questioner asked about the risk of data loss of digital collections due to accident or obsolescence. Dr. Beeman acknowledged the risk and noted that there are efforts to replicate digital collections, but the effectiveness of these programs is not known. Future-proofing is even more of a challenge due to the NSF funding paradigm of 5 years plus a potential 5-year extension, meaning that initiatives it funds necessarily focus on this time frame. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the Society. At 10:08 p.m., President Milstein adjourned the 2,376th meeting of the Society to the social hour. Temperature, 15°C, weather clear, attendance, 58. Respectfully submitted, Preston Thomas, Recording Secretary.
Thank you, Preston. Are there any comments or corrections to the minutes? Well, hearing none, I'll thank Preston for pronouncing. I wasn't ready. Do I have a motion to approve the minutes as read? I have a motion. Do I have a second? Second. All members in favor? Aye. All members opposed? The minutes are unanimously approved and will be posted to the website in due course. As measured at the meeting before last, the 36th meeting of the Society was held on Wednesday, 11 December 1872, a few days earlier than was customary at the time, for the purpose of introducing Professor John Tyndall of the Royal Society. So I'm going to take a few minutes to say a bit more about Tyndall than I did at recounting this meeting, because he was a remarkable scientist. And his visit to the Society and their change of the date of their meeting shows how important the meetings were at that time to the exchange of ideas and the dissemination of scientific results and thinking. The bulletin does not report when the meeting was called to order or its location. President Henry presided. As many of you know by now, Joseph Henry was the primary founder of PSW and its longest-serving president. He led the organization from 1871 until his death in 1878. That's the wrong slide. That's Henry. He was the preeminent American physicist of his time, known internationally for his pioneering work on electricity and magnetism, particularly his work on induction, which led to the invention of the telegraph and the telephone. Among other important roles, Henry served as the founding and first secretary of the Smithsonian Institution. As related in my first recounting of this meeting, Henry and Tyndall discussed the effects of fog on the transmission of sound. Simon Newcomb updated the Society on plans to observe the Venus transit. And W.B. Taylor read a paper on waves, molecules, and atoms in which he discussed the ether. But the highlight of the meeting, no doubt, was the opportunity to meet with Tyndall. Tyndall was a remarkable scientist. He made important contributions in many areas of science. He wrote about, the one that does everything, the blue one on the right. Yeah. He wrote about 150 scientific papers and at least 12 books, many of them textbooks intended for non-physicists. He discovered the Tyndall effect, the scattering of light by suspended particles, and he devised methods to measure the effect. He used these methods to measure the amount and characteristics of the particles in liquids and gases, and having invented methods to measure them, he developed ways to remove them from solutions and gases, including a kind of fly paper technique that trapped them. He used the technique to produce optically pure air. The slide shows a sealed box. The interior walls are coated with glycerin to trap the particles. The box also contains a collection of tubes containing broth to support bacterial growth. Tyndall first found that the media in the tubes remained free from growth in the pure air, but later experiments failed. As he later found, the growth in sterile broth in the later experiments was due to spores in the broth that were not killed by heat and pressure sterilization. Carl's probably going to correct me at some point. So he invented Tyndallization. He invented a technique for sterilization that finally put to rest the idea that life can arise by spontaneous generation. That is, that life can come about on its own without familial descent. In essence, sterilization techniques at the time were applied once and failed to kill spores. Tyndall showed that carrying out a series of sterilizations in succession, each one separated from the next one by a relatively brief incubation favorable to living growth, produced solutions that did not support spontaneous generation, even on prolonged incubation under conditions very favorable to living growth. Tyndall and Tyndallization are considered to have provided the definitive scientific proof that spontaneous generation does not occur, something we take for granted today. Tyndallization itself is still in use today in some applications. And as I pointed out, the slide shows a Tyndallization box with sterile media. The serpentine tubes allowed air into the sealed box, but it kept out bacteria and spores. And the observing tube allowed Tyndall to monitor the purity of the air. It's worth noting that Tyndall's results did not receive an entirely friendly reception, even in the community of scientists. But the consensus among scientists at the time was that God could create life spontaneously. He was, as seen in this caricature from Vanity Fair, even ridiculed in some quarters. While most scientists today do not take the idea of spontaneous generation seriously, in the sense of fully developed organisms coming into existence from nothing, as it were, by the hand of God, there is a general belief among scientists that life arose on Earth from non-living matter by physico-chemical processes that likely occur in many places throughout the universe. Tyndall was a pioneer in the study of infrared radiation and carried out extensive and detailed experiments to determine its interaction with matter. He is particularly noted for using the methods to determine the relative infrared absorption of numerous gases, including nitrogen, oxygen, water vapor, carbon dioxide, ozone, methane, and other gases, and for determining their heat capacities. Based on these results, Tyndall concluded that atmospheric heat is determined by abilities of the gases in air to absorb infrared radiation. In the course of these studies, he determined that water vapor is the strongest absorber of radiant heat in the atmosphere and is the principal gas controlling ambient temperatures, something that's still understood to be correct. And he found as well, again correctly, that absorption by the other atmospheric gases is small in comparison, although not entirely negligible. Tyndall thus provided experimentally determined properties supporting the greenhouse effect of the Earth's atmosphere that had at that time been postulated by others. Obviously matter important to the current modeling of climate and climate change. This slide is a contemporaneous drawing of an apparatus he used to study IR and its interactions with matter. And these are just a few points of his prolific and seminal work. We now turn from the 36th meeting that took place in 1872 to the 2,377th meeting taking place tonight in 2017, and to tonight's lecture. And it's my pleasure to introduce tonight's speaker, Eric Lindstrom. Eric leads the climate-focused area of NASA's Mission Science Directorate. He serves as co-chair of the International Steering Committee for the Global Ocean Observing System and as a scientific consultant to the National Geographic Society on ocean atlases and books. He is particularly interested in ocean circulation and air-sea exchange processes, and he has engaged extensively in seagoing oceanography and remote sensing projects to study these and other ocean-related phenomena. Eric has pursued his research throughout the world, and his pioneering research on circulation of the western tropical Pacific Ocean in the region of New Guinea is particularly well known. In recent years, he has taken NASA to sea in projects marrying NASA satellite observations with seagoing oceanography. Eric is the recipient of the American Geophysical Union's Ocean Sciences Award and several NASA medals for exceptional service and achievement. He earned a BS in Earth and Planetary Sciences from the Massachusetts Institute of Technology and a PhD in Physical Oceanography from the University of Washington. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Eric to the podium.
Thank you very much, Larry. It's a pleasure to be here. I met some of you in the audience, and I hope I can live up to your expectations for an interesting talk here this evening. Let me preface the talk with a little more of an introduction to myself, because you see a guy standing up here who's from NASA headquarters, and you think satellites, and I don't think of myself as a satellite guy at all. I spent half my career going to sea in an intimate interaction with seawater directly, and moved back to the United States after 10 years in Australia to help organize the World Ocean Circulation Experiment, which was a lot of ships going to sea to try and map the whole globe. And I think that's where somebody at NASA saw me and said, I was sitting in an office in Silver Spring one day, and I got this call. It said, how'd you like to run NASA's oceanography program? It took me 1 nanosecond to say, yeah, I'll do that. That sounds cool. I went over and I said, well, do you realize that I have never looked at a piece of satellite data in my entire life? I know nothing about satellites. And they said, that's okay. We don't need you for that. We need somebody who's touched seawater. So here I am 20 years later. We still have many, many oceanographers in NASA who've never touched seawater, yet they call themselves oceanographers. And my job is really to bring the natural science of oceanography together with the modern technology and make the most for science and society out of this marriage. So that's what I wanted to talk with you a bit here tonight. I'm going to start off with being silent for 5 minutes and letting you watch a little movie that will kind of give you the grand spread of what the oceanography from space looks like. And then I'm going to spend some time going through some of the societal implications of the ocean measurements and hopefully some good graphics that you'll appreciate. And once that's over, I'm going to do phase 2 of the talk, which is to go into a little bit more depth into sea level rise and the melting of the Greenland and Antarctic ice sheets by the ocean and those implications. So I hope that gives you an outline and you can sit back and relax, and we will go forward with this.
Earth is the water planet. Although 40% of Earth's population lives within or near coastal regions, the ocean impacts people everywhere. Most of Earth's water is stored in the ocean, a driving force for weather and climate. The Earth's surface is warmed unevenly by the sun. Heat, a form of energy, helps drive ocean and atmospheric circulation. The ocean absorbs and stores more heat than the atmosphere. Both the atmosphere and ocean move heat. The atmosphere does this quickly, the ocean slowly. At the ocean's surface, winds drive currents. Multiple forces keep the global ocean conveyor belt, or thermohaline circulation, in perpetual motion. Below the surface, deeper currents are driven by differences in density. Mixing and upwelling in the ocean, transporting nutrient-rich waters to the ocean's surface. Nutrients sustain biological productivity in the ocean. Extreme variations in sea surface height and sea surface temperature affect ocean and atmospheric circulation. El Niño and La Niña occur when changing wind patterns displace warm and cool water in the equatorial Pacific. Both have global impacts. During either of these events, the replacement of cold water by warm water leads to air temperature swings and changes in humidity. This alters weather patterns by steering storms and rainfall to new locations. Shifts in rainfall affect plant growth and areas impacted by drought. When heat is exchanged between the ocean surface to the atmosphere, it influences climate. For example, heat and moisture carried by the Gulf Stream northward bring warmer temperatures and a moderate climate to Europe. An eddy is a circular moving body of water that spins off a main current. Eddies play a major role transporting heat and nutrients. Thunderstorms are a frequent occurrence in the tropics. Some of these may become organized into large rotating systems with strong winds growing into tropical storms or hurricanes. Tropical ocean basins like the Caribbean and the Gulf of Mexico retain substantial heat, making these regions favorable for rapid storm intensification. By extracting large amounts of heat from the ocean, storms can become massive and destructive hurricanes. a driving force for weather and climate. The ocean is essential to life on Earth. It is the primary storehouse of Earth's water. Without the ocean, our planet would be uninhabitable. NASA satellites and their unique view from space are helping to unveil the vast and largely unexplored ocean.
Okay, so that's the talk condensed into 5 minutes. I'm going to try and go back into some more depth in some of these data sets, and you'll see some more and some of the same ideas emerging. So I thought that really captures some of the primary areas at which we measure the ocean: the sea level, the winds, the temperature, the ocean color, which gets us about life in the ocean. We can now measure the surface salinity of the ocean from space. That's pretty cool. I'll go into that. That wasn't in the movie. So there's a lot to be derived in terms of societal benefit from these measurements. Back to the real start of the talk here. So the ocean gives us, and what we see is protein, the fisheries, minerals, salts. There's also ocean mining for manganese nodules beginning in the depths of the ocean. Transportation is big. 90% of the goods that we have in the United States come by ship across the sea. And there's increasingly energy from the wind. The oil and gas industry, of course, has a big stake out in the ocean. And so all of these sectors, fishers, miners, transportation, energy, all call on oceanographers to help with their business and economics. So there's many practical applications for the science. The pressures on the ocean ultimately come back to the population on the planet. The ocean is a place that we put our pollutants to diffuse them into the vast ocean. We expect it to give back an unlimited supply of fish, but we've already fished out 90% of the big fish in the sea. We're working on the last 10%. So people in the audience here, you'll probably be the last people on the planet eating sushi. I think that's it's probably going to end here within the next 25 years. And we dump plastics and all sorts of things in the ocean, which I'll go into. So we're worried about our ocean. It's not the infinite resource and sink that maybe you were taught back in your earlier school days, and it's very important economically. So NASA is much more than the astronauts, I'd like to say, but we don't get much press in the Earth science. The Mars mission is getting all the press, and then understanding and protecting the home planet is in NASA's charter, and we do that with a fleet of Earth-observing satellites. It's population in low Earth orbits, about 20 satellites that look back at the Earth. And we have probably about 20 in the build planning phase at any one time, so to maintain this fleet of 20 satellites. And here, they're depicted as flying acronyms. Only in Washington could we have that. These are the acronyms for all the satellites that we have on orbit. It does kind of faithfully depict where they are in orbit. Most of them are in polar orbits. They go around the Earth and they cross the equator at the same time of day and evening as the Earth rotates under them. The International Space Station, ISS, is in an equatorial orbit. It goes around this way. Then there's the A train here, a whole bunch of satellites that measure land properties and atmospheric composition. And they all want to take the measurements at the same time so they can play them off against one another. So they cross the equator at 10:30 in the morning every day. They're called the A train. And then we have some oceanographic satellites, the JASON satellites, which you'll see more of in the talk. They fly in a special orbit that's inclined from a polar orbit so that we don't have the tides interacting with our sea level measurements. And then there's the Aquarius and SMAP, that's the Soil Moisture Active Passive Mission. They fly along the Terminator with a 6 a.m., 6 p.m. orbit because they measure salinity of the ocean, and we can't see that in the daylight. The sun is a big interference, so they have to look down on the night side of the Earth, but they need to be powered, so they fly on where the day-night boundary is around the Earth at all times. So it's getting hot in here, planet Earth. We have been measuring, perhaps for the longest time, sea surface temperatures from space. We measure in several different wavelengths. We use infrared, which can't see through clouds. We'll come back to Tyndall all the time. The water vapor in the atmosphere is a barrier to some remote sensing, and so we have to correct for it both in altimetry and with sea surface temperature. This is about a 2-year segment of temperature that combines the best of what we can measure with clouds and then fills it in with microwave sea surface temperature, which is less spatial resolution on the ocean, but it can see through clouds. So we can magically take all the clouds off the surface of the Earth and see the sea surface temperature. We can see things like the upwelling along the equator and the tropical instability waves. We can see the Gulf Stream and the warm waters that come out of the tropics and head up towards Europe, keeping it warm, as you heard earlier. There's a similar current, the Kuroshio off Japan, which keeps the North Pacific warm. There's similar western boundary currents. They're called off of Australia, the East Australia Current, and the Agulhas Current off of Africa, and the Brazil-Malvinas Current over here off South America. And then you can see the major upwelling zones where your food, your protein, comes from off South America, where cold polar waters make it up along the continental boundaries. Here off South America, and then another big upwelling zone, very productive region of the world fisheries off of Namibia and South Africa. Eddies are a constant in all the ocean. You can see the major current features, but there's this chaotic nature of the ocean circulation, which makes it hard to measure from a ship. You know, you go out and you're out for a month and all you see is one eddy and you get all confused about what the currents are actually doing. So the great benefit of observing constantly from space is that we can kind of average out all the eddy circulations and begin to or in fact measure them all, as we're doing now. We have high resolution models. We want to measure them all and we can take them into account in climate. So in addition to getting warmer over time, 90% of the greenhouse heat goes into the ocean. The ocean is also getting sour. It's getting acidified by the dissolution of carbon dioxide into the ocean. The ocean is now 30% more acid than it was at the beginning of the Industrial Revolution, and this has effect on sea snails that are at the, near the bottom of the food chain in the ocean. This shows ocean acidity as it will be in 2100, what it does to a sea snail after 45 days. It basically dissolves them over time. And so life is going to be really difficult at the bottom of the food chain in the ocean in 100 years, because the chemistry of the ocean is changing so fast compared to what it would do in a non-human filled world. It's as if an asteroid hit the planet or something and changed the chemistry of the ocean. So that's the way I kind of think about the human race and its effect on the ocean, as equivalent to almost an asteroid impact in what it's done to the chemistry and the changing temperature of the ocean. It's a massive effect happening in a very short period of time. So some of the other effects that are going along due to the warming is that you may have heard about the retreat of the Arctic sea ice area. This is the minimum. It happens in about September every year. And we were going along measuring relatively small changes in the minimum area of sea ice until into this millennium, and it started going down a lot more quickly. The amount of sea ice really, it was 2007 that we noticed this, big dip in that we were losing sea ice. And it's even worse than it looks, because that's showing the area of sea ice. And the sea ice in the Arctic used to have a large percentage of very thick multi-year ice. And it's almost non-existent. It's gone extinct. Most of the ice up there is 1 meter thick seasonal ice. So that's only along the northern Canadian boundary up here that you'll find still remnants of multi-year ice, which used to be common. So the thickness of the ice has changed dramatically. So the volume of ice is much less than it used to be, and is in worse shape than this area diagram would indicate. So it isn't just sea ice that we can measure changing from space. We can also measure the changes in the mass of the major ice sheets. We have a gravity mission which measures the changes in gravity as the ice loses mass and turns into sea level rise. And so here in Greenland, the amount of mass loss is about averages 280 gigatons of ice a year is melting into the ocean. And it's mainly along the southeast and southwest coast. There's still relatively little melting up in this area and in the core of the continent. We really worry about the health of the Greenland ice sheet, because if it all melts, sea level gets 6 meters higher, 20 feet higher. That's going to impact places like Florida, which are as flat as a pancake, in a big way. Well, it's going to take a long time for an ice cube just exposed to air to melt. So maybe you'd think, okay, it's not going to take long. But a lot of this ice here, this rapid melting is happening because the ocean is exposed to the glaciers. It's melting them back with water, which is a much better conductor of heat. And then a lot of this part of Greenland is below sea level. So if we melt them back far enough, the ocean pours in under the glacier and it'll be exposed to water and it will melt quickly. So, that's the catastrophic possibility. Right now, and I'll show you a little bit later more details on what we're doing in Greenland to measure the ice changes. Similarly, in Antarctica, but not so much, there is warming in the West Antarctic ice sheet, where this ice sheet also has a major portion of it sitting under on land that's under sea level. So as the front melts off, the ocean can get under this glacier and cause rapid melting. So overall, these two ice sheets contribute about 1 millimeter per year of the 3 millimeters per year that sea level is currently rising. So a third of the present sea level rise is caused by these two ice sheets. Another third is caused by mountain glaciers melting right now in Alaska primarily and the Himalayas. And, what's happened? We quit. I don't know what's happening here, but we'll try and get restarted here. Oh, yes. Okay, I'm going to try and go. I no longer can see what's on the screen, so we're going to carry on here with. So here's the grand picture of how much we're losing, what the sea level equivalent is of Greenland and Antarctica. Mountain glaciers are another 1 millimeter a year approximately, and the warming of the ocean is the other third of 1 millimeter per year of sea level rise. So equal thirds, the major ice sheets, the mountain glaciers, and warming of the ocean. The background level of sea level rise back a century or so ago was 1 millimeter per year. So we've already tripled the amount of sea level rise that we've bought coming into this century. And it will increase. Okay, so we measure sea level rise directly using a satellite altimeter. We started in 1992. We've been measuring continuously ever since. This actually simulates, going back to 1950 up to 2009, what the anomalies in sea level look like. So this is not showing you the mean ocean circulation. It's showing you things like El Niños, which are these big, when it turns big red blob, that's a big sea level rise high, where it's warm water in the tropical Pacific. Those occur every 3 to 7 years. It's like a foot of extra sea level. It causes the whole pattern of convection in the atmosphere to move around the planet, which sort of rings the planet like a bell. So the weather changes in California, the East Coast, in Alaska, everywhere when there's an El Nino or La Nina. So it starts in the tropical Pacific, and we can measure it, what's happening with El Nino, very well with the sea level measurements. In fact, we produce a sea level map every 10 days of the Pacific Ocean and issue it out of the Jet Propulsion Lab. If they miss by a day, they get phone calls from people who want their sea level map. And the first people, we learned this really quick, that these people called and said, "Where's my map? I got to make some business decisions." Well, who are you? They were roofers in California. And they would use these maps to tell whether there were going to be winter storms in the coming season ahead. They could do their own El Nino forecast. They didn't need to wait for the Weather Service. They could look at the sea level map and say, "Oh yeah, storms in California, that happens every El Nino year." They could stock up and prepare for the heavy business of repairing blown off roofs in California. So that's where we go from, science to direct applications, and that's really heartening. But these stories don't get out. There's a lot of them like that. And so when we can tell the story of climate in a way that hits people's pocketbooks, it really makes a big difference. So this altimetry has gone on for 25 years, and we're planning the satellites and building them now that will take us out to 2030. It's so economically important to society to have sea level and climate measurements integrated by the ocean that we will continue in just about any budget environment. So this is what these satellites, starting with Topex Poseidon, a NASA French initiative back in 1992, the Jason series of satellites. Jason, it gets its satellite name, Jason, from Jason and the Argonauts. Argo is a fleet of 3,000 profiling floats in the ocean that measure the temperature and salinity of the upper ocean. So they are coupled together. The Argo floats tell us the amount of heat in the ocean. Absolute sea level is told by the JASON satellite. So JASON and the Argonauts, they're our main observing system. So as I told you here, you can see the from GRACE, which is a pair of satellites that measure the distance between them. We can get the gravity field on the Earth, and we can watch the mass change of the ice sheets or how water moves around on the planet. They give us that 2 millimeters per year of change from the ice sheets and the mountain glaciers. And the remaining 1 millimeter a year difference between that and the absolute sea level from the JASON series is the heat from in the ocean that's measured by the Argo. So we have all the components of the observing system working together for us. Okay, so sea level is not a bathtub. It isn't rising the same rate everywhere in the ocean. In some places, it's rising faster in the Western Pacific. Off of California, it's been actually going down, but it will reverse. There's something called the Pacific Decadal Oscillation. So the Pacific has this rock and roll it has going. About every 10 years, it shifts. And so it looks like sea level's rising faster in the West Pacific and falling in the over in the east, but an oceanographer will say, hey, that's not going to last forever, guys. Sea level's going to go way up in California quickly when the Pacific Decadal Oscillation shifts. So that's an interesting game we play, you know, forecasting for the next 10 years. So the water cycle is key in studying the climate and the ocean. A lot of people in NASA who study the water cycle only study the water cycle over the land and fresh water. I don't see how you can study the water cycle without studying the ocean. You'd think that's where most of the ocean is. And in fact, it's a pretty interesting story that we get about the water cycle in the ocean. Salinity at the surface of the ocean is very much connected to evaporation, the difference between evaporation and precipitation. So if more evaporation, it gets saltier. If more precipitation, it gets fresher. So in the 2000s here, starting in 2011, we launched a satellite which is able to measure the surface salinity of the ocean. And this is the time series movie. It's like watching molasses pour. But you know, if you're an oceanographer, you love this stuff. You can see the big features like the Amazon River plume, the fresh water that comes out into the Atlantic from the largest river. You could also see the Orinoco. You can see an occasional bit from the Mississippi up here. But the main features of the ocean are the subtropical high pressure zones, which are clear, and where the deserts are on land, we have evaporation in the ocean, and we have the saltiest places in the ocean, in the mid-latitudes. And then we have rain in the tropics under the intertropical convergence zone and at high latitudes in both hemispheres. And it's desert over on this side of Asia, and then all the rain and runoff here in the Bay of Bengal. So there's a major piece of the atmosphere which is convecting clouds here, a lot of precipitation. In El Nino, this whole cycle sort of moves over into the Pacific and causes the atmosphere circulation to change so much that we can make these grand climate predictions. So this is a wonderful story. How do you measure salinity from space? You measure the changes in L-band microwave radiation from the surface. It's radiation at 1.4 gigahertz. It's the same as you use for GPS. And it varies enough that you can measure the salinity of the ocean. So we are on this idea of, well, let's measure how the places in the ocean change. Here's the map that I just showed you with the highs in the mid-latitudes and the lows elsewhere. This is the mean salinity. Well, if you look at all the salinity data that's been collected on the planet for the last 50 years and take the trends, you'll see that the salty places are getting saltier and the fresher places are getting fresher. That's the exact fingerprint you would think of if you have a warming planet and you're accelerating the water cycle. The ocean is integrating that out and telling us, indeed, that we're having drier weather over the ocean where it's dry, and it's rainier where it's been rainy, and the ocean is telling us that. So that's a pretty fabulous observation, and it backs up the climate model. So this is where these ideas of more severe weather, rainier places will get wetter, and drier places will get drier. It's hard to see over the continents because it's so noisy, but the ocean tells us the story pretty well so far. Here's a nice movie of the hurricane season from June to November in 2011. With the background color is sea surface temperature, and it's overlain with the winds. Both of these things we measure from space. And I'm putting this on because you've already probably heard about hurricanes and how they extract heat from the ocean to power themselves. Well, you can see that for sure in this. If you watch here as we get into August, you'll see the swirls, big swirls of hurricanes here, and they will leave a big yellow wake behind them as they extract the warm sea surface temperature to fuel their development. So hurricanes usually get started over here with little waves in the wind from coming off the African continent. We see them first in the wind field before you actually see them as pressure signals. So the meteorologists use these wind fields to see where the hurricanes are developing, and they can get 4 days to a week lead before you actually see a pressure center of a hurricane. But these are the sorts of waves that develop, and then they'll, as they get over warm water, they'll start curling up and heading off to high latitude. So this is, when I show graphics, this is people's favorite, actually. It's kind of a poetry in motion. And we're getting here into August. So the action is really mostly in August and September here. Get ready for it. Wake up. They're coming along here. This one is going to go. That's a hurricane. Here comes another one. This is a big one. So we can see these wakes in temperature. Now that we've measured salinity for a few years, we can actually see the wakes of hurricanes in the salinity field as well. And places, there's interesting interaction where the Amazon River comes out. The water's warm here, but it'll get capped off by a layer of fresh water, and the hurricanes go over it, and they can't extract the heat because they can't get past the fresh water at the surface, making water too light for them to mix down. And so even though there's warm water, if it's fresh enough from the Amazon River plume, they won't develop as fast as someplace, say, over in the Gulf where there's a lot of warm water exposed right at the surface. So air-sea interaction is a lot more interesting now that we have temperature and salinity from space. Okay. So we see this in not just in hurricanes, but there's interesting air-sea interactions. There's these what they call atmospheric rivers these days. They've been going on for a long time. Somebody finally decided to name them. They look like there's moisture coming directly out of the tropics up into California. And there are some historic floods in California where this pattern just gets set up and it will rain for months into the Central Valley in California. This whole thing looks dry there. That can become a lake. The whole Central Valley that feeds the United States there with all the vegetables and fruit, that can become a lake. It did in 1865. Sacramento was under 10 feet of water from these atmospheric rivers. So there's a lot of study going on into them at the moment because you saw this last year what a few atmospheric rivers did to California, and it's quite possible that that kind of pattern could be set up again. It just hasn't happened in our lifetime. Our lifetimes are really short. So all this data, sea level, winds, contribute to our knowledge. We can actually see tsunamis from space now. And another interesting phenomena that causes a lot of havoc here from the Sumatran quake in 2004, Hurricane Sandy from one of the hurricanes brings seawater ashore, and then the Japanese tsunami in 2011. It particularly, we've done a lot of study, I'll show you that in a minute, of the debris field, and that's causing us to do a lot more work on plastics in the ocean, all the debris that came out from the unfortunates that were part of that destruction. But there's a lot of debris in the ocean.
Plastic, 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 plastic. Piece of wood, plastic, 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 plastic. It doesn't matter where you point it.
Well, as a sailor, I've always been aware of marine debris. Walking my dog on the foreshore at home, I'm always surprised how much there is. You couldn't possibly keep pace with it, trying to collect it.
The marine debris becomes blindingly obvious to you when you're near the areas of major population.
I think the most surprising thing for me has been the amount of debris we've seen very, very far from land. You know, in the Southern Ocean, I mean, we're basically as far from man as you can be. And I remember at one point we were watching some seals, and then one of the girls who's up the rig is like, oh, look at that seal. Oh, it's a seal playing with a plastic bag. Definitely makes you realise the impact we're having.
One thing that sailing around the world does is it makes you realise just how small our planet is. If we can sail all the way across the widest ocean in 2 to 3 weeks in our small boats, that means the ocean isn't that big and we need to protect our seas.
The ocean is a big rubbish. There is too many.
How people in the world can't treat the ocean with more respect is just fully beyond me.
If we can just bring out the message how dirty the oceans are getting. It's not funny anymore.
No, it's not funny anymore. I spent 40 years going back and forth across the ocean, and the vast tracts of life in the sea have been replaced by floating plastic. It's really depressing. So we need to try and do a better job of our stewardship of the ocean. It's a limited resource. It's not the big, infinite resource that you would like it to think it was, that will constantly produce food and constantly take up our garbage. I'm going to talk a little bit more about the circulation of the ocean. Here we use the height, and I'll go into this more in a few minutes, of the ocean and the winds to produce a measure of the surface currents of the ocean. And so you can see the major currents, the Gulf Stream, the Agulhas, the equatorial currents, the Great Whirl off Africa, the Kuroshio. So I love all these ocean currents. I've been out in many of them. The so-called garbage patches of the ocean, where there's convergent currents and a lot of the plastic tends to accumulate, are in these same places the salinity is high in the mid-latitude, mid-tropical gyres. And I was just out here 6 months ago. There was a lot of floating plastic bottles. In these mid-latitude areas, they tend to sort of get broken down into microplastics. There's a lot of the plastic that we put in the ocean gets broken down into smaller and smaller pieces, and then it can get ingested into the food chain. So there's a lot of fish and birds with that have plastic inside of them now. So we use these current systems to try and say where debris is going. You may have seen this last on the background of CNN during the Malaysian aircraft downing in the Indian Ocean. They use these currents to try and determine where debris would have gone. In fact, yes, about 6 months later, debris started showing up in Madagascar as the ocean modelers predicted. So this plastic degrades. There's a lot of big plastic following things like the tsunami in Japan. So that's made for a couple of years of big debris experience, but there's a lot of micro debris in the ocean now. We're putting 8 million metric tons, it's estimated, of plastic waste into the ocean net every year. Somebody just came out with a paper that if we keep up at that rate, there'll be more plastic in the ocean than fish by 2030. So we're not doing a small number on the ocean with our failure to recycle. Ships at sea don't dump anymore. It's been illegal since the 1980s, so most of the plastic in the ocean comes from land-based sources, not from people polluting at sea. In fact, mariners are really they see it all the time, so they're really good about burning and recycling and not putting anything over the side that shouldn't go over the side. It's the landlubbers that really own this problem. Here's a simulation of the movement of the marine debris from the 2011 tsunami. Use the currents, and then there's the debris with different windage is marked here. So in red, here are things with high windage that sit way above the surface of the water, and the low windage, things that sit right at sea level, have low windage, and they wind up in different places. So this model predicted that we would find the big debris on the Alaska coast, and progressively smaller debris down the west coast. And in fact, by beachcombers going along all those areas, that was proven to be true. So the model works. And then the guy who did this model is living in the Hawaiian Islands. He wanted to know when the debris waves are going to show up, and he's been making a big name for himself in Hawaii by predicting when waves of tsunami debris are going to come ashore. They're still coming ashore in Hawaii 6 years later. Okay. So what have we discovered here from this part of the talk? My message is the ocean is large, but it's finite. We can observe the human impacts on the ocean in many ways. The ocean is a great integrator of mankind's engineering of the environment, whether it's with heat or carbon dioxide or plastic or many other things here. We can see our effect as engineers of the environment. Thankfully for all of us, the ocean absorbs much of our excess heat. Things would be a lot worse if we didn't have the ocean, so we are blessed. There's still room, for us to put sewage and other things in the ocean. It's still the best place to put a lot of those things. But there are consequences of doing that. So it needs to be a conscious decision to use the ocean as a reservoir for the throw-offs from society. And we really need to conserve that, the ocean's ability to do that. What we can do is be a better steward with our recycling and what we eat from the sea. Go to the Monterey Bay Aquarium website and find out what a sustainable fish is to eat, and be sure and watch out for your plastics. Make sure you recycle your plastics. Don't let them go anywhere but someplace where they can be disposed of on land. It's going to pay off. We can't manage all this ocean if we're just going to put our head in the sand and ignore all of this. Our mantra in the Global Ocean Observing System is we cannot manage what we do not measure, observe. So we're all about observing the ocean. I'm not in a policy agency or a regulatory agency. My job is just to collect the information. I'm just telling you what I know. You guys have to figure out what to do with it. So I believe a highly educated workforce and public is needed to maintain and expand our ocean observations and to be good stewards of the ocean. So I thank the Philosophical Society of Washington for inviting me to share my passion for the ocean with you tonight. So this is where I was going to conclude a talk, but if you have 15 more minutes, I'm going to show you a little bit more about sea level. How are we doing with that, Larry? Okay, cool. So skip the questions for now. And I have to load the other talk. So satellite altimetry measuring the sea level of the ocean from space I was going to tell you a little bit technically how it works. Is we have the satellite up at 1,300 kilometers altitude, about 800 miles above the Earth, and it's making an orbit every 90 minutes, and it manages to get to every place on the globe to measure sea level about every 10 days. And it measures the range between the satellite and the ocean surface. Well, that's not enough to tell us what sea level is. We have to know the exact position of the satellite, and we have to correct for the gravity shape of the ocean, which goes up and down, 60 meters or so over seamounts and stuff. There's sort of a fixed, weird shape of the ocean. And then the ocean dynamics and the currents and all the stuff that we really care about is about 1 meter on top of all these changes in the sea level. So we locate the satellite with a whole bunch of different systems, GPS orbits and laser ranging from the ground. It's got laser retroflectors on the satellite. We use another thing called DORIS, which is a lot like GPS. It's the French land-based version of GPS. And all these things, we can measure where the satellite is to within a millimeter, right? So we're measuring, millimeters of sea level accuracy. So the accuracy is about a centimeter from 1,300 kilometers. It's like measuring less than the thickness of a dime from the tallest skyscraper. It's just amazing what we can do. And so that gets all transformed into sea level. And we've been able to do it so well that we can watch the ocean rise at 3 millimeters per year. That's all within our, definitely within our error bars now. So the main reason we measure sea level is so that we can measure the slope of the sea surface, because the difference between highs and lows is much like in the atmosphere. Between high pressure and low pressure, there are winds. So it's the ocean currents we get by differencing the sea level between one place and another. This is in the northern hemisphere. If it were in the southern hemisphere, the rotation of the Earth means the currents go the opposite direction. So it's a fictitious force that the Coriolis force, the balance between the Coriolis force from the rotation of the Earth and the difference in pressure, which cause the main ocean currents in the ocean. So measuring sea level is really a simple cause and effect here. As we put the CO2 into the atmosphere, It's a radiatively important gas like water vapor, and it stores more heat in the atmosphere, and most of the heat that stays in the atmosphere because the CO2 goes into the ocean, so the ocean rises. So there is a direct correlation between the rising CO2 and the rising oceans. So not only is the heat trapped by the CO2, but the CO2, about a third of that goes into the ocean and causes this ocean acidification. So there are both of these problems, both heat and acidification caused by the CO2 in the atmosphere. So we measure the rising oceans. It's thought that worldwide 200 million people live on land that will be regularly flooded or below sea level by 2100. So that's going to cause a lot of problems. I'm planning to retire to the beach in Southern California. I may be living in hip waders, you know, if I were alive in 2100. But, you know, we already are used to seawater in our front yard during El Nino years from the storms sending water over the beaches into our coastal homes in Southern California. So it's really no surprise to me that more and more places are going to be seeing that. Certainly in Seal Beach, California, such events have been going on for decades. So we've had a number of altimeters going along. First TOPEX, Jason 1, Jason 2. We have Jason 3 on orbit now, and then there's Jason 4 and Jason 5 that are being built right now. So those are carrying on this important measurement. So this sort of touches on some of the science that we get out of it. It was used in Deepwater Horizon. Here's all the tracks from the sea level. You can track the oil spill by measuring the currents using the sea level, incorporating it all in models. Also measuring the temperature in the upper ocean. The amount of heat in the ocean causes sea level to rise. So hurricanes tend to intensify over high sea level, and so the Hurricane Forecast Center uses the sea level maps to try and predict changes in hurricane intensity. It works really well. And then we monitor the El Nino, as I mentioned, with roofers in California. They get these maps, and they can look at these maps and say, oh, I need to change my stocking strategy for asphalt shingles. So the patterns change here. This is the current trends in sea level from 1993 to 2015. So it's rising fast in the Western Pacific. There are a lot of island countries out here with close to sea level that are feeling the impacts, and communities are actually having to move out of their islands and move to New Zealand and so on. So they're really bearing the brunt of it at the moment. And then it's not rising so fast here off California. But this pattern could be shifting, with the changes in the overall climate of the tropical Pacific. There tend to be these swings over 10 to 20 years in the ocean circulation in the Pacific that lead us to believe that this is a relatively temporary phenomena of a couple decades duration. So the El Nino updates come along every 10 days. And Bill Patzert at the Jet Propulsion Lab in Pasadena is very famous within Californians as the climate guy who tells them whether it's La Nada or whatever he wants to call the latest, characterize the El Nino maps. There's increasing effort to, get coastal currents out of the sea level measurements, and scientists are always trying to extract the last little bit of information out of such data. So I don't need to go into that, but it isn't all just around the U.S. There are a lot of publications on all the major current systems using the altimeter data. What I wanted to get to here was the number of publications that the scientific community, we have over 4,000 peer-reviewed public articles for using the altimetry data. We have an ocean surface topography science team constantly at work on data, producing more than 200 papers a year at the moment. And so the science results from this system haven't diminished at all over 25 years. They've just been increasing. And finally, sort of a playback to the Tyndall and the previous meeting back in whatever, 1871 was it, or what? 1872, sorry. Got that wrong. I must be wearing out here. But the corrections, one of the major corrections that we have to apply to sea level measurements from the radar is that we have to have a radiometer on board to measure the water vapor in the atmosphere. It's the major correction to the radar signal. So as a byproduct of our altimetry, we've been measuring the water vapor in the atmosphere very closely over the 25 years. And it's a noise for us that we take out, but other people study that signal. But it's the resonance back to 1872 is amazing. That the key to getting these millimeter per decade error bars on trends in sea level come from making accurate water vapor measurements in the atmosphere, and we have to get them correct, otherwise the trends of sea level would be wrong. So we're putting better and better water vapor radiometers on our altimeters so that we can keep the accuracy of the sea level record going, because it makes a big difference out here in the future what the trend is going to be, how much acceleration is there in sea level. So that's what we pay critical attention to. I just wanted to show, I showed this earlier of Greenland, but I got an updated picture here of, is this going to play? It's not going to play, okay. I can make it play. This picture of Greenland has the ice flow measurements on it here, the ice streams. The ice flows just like water flows. It's a very solid liquid. And so as it melts around the edges, the ice flow in the interior increases and the ice flows towards the ocean when you take off when you melt it around the edges. So we're spending a lot of effort studying Greenland because it's melting so fast. So we have this project that started last year called Oceans Melting Greenland, OMG. 5-year project. Josh Willis at JPL is the principal investigator. And the idea is that the ocean circulation models show that the warm water around Greenland is causing this ice melt along the edges. And so the overarching science question is, to what extent are the oceans melting Greenland's glaciers from below? And so we want to know how much Atlantic water is getting into all these fjords and up against the ice. So we need to study the process of how warm water transfers from the ocean into the glacier faces. And then what is the volume change of these marine terminating glaciers? So we have a 5-year project to track the spread of the warm water and to quantify the changes in the ice in these glaciers. And it involves repeated flights with aircraft to measure the temperature and salinity of the warm water that's below the surface that goes up to the ice face, and then a radar that measures the topography, changing topography of the glaciers every year. So we have 4 different years of ice measurements. We're getting the bathymetry in all of these fjords once so we can do the modeling. And then measuring the ocean every year for 5 years with air-launched expendable temperature and salinity probes. And so we'll be able to look at the change over 5 years from how this warm, salty water encroaches into the fjords below the cold, fresh water. These transect along this one particular fjord. And so the water is there at 400 meters is what we know from historical data. It's already as warmer 3 to 4 degrees than there are significant changes in the warm water getting in, and we'll be able to model it once we have the topography of all these fjords. So, and then they measure the thinning of the ice edge at the glaciers, and thinning of 50 meters per year occurred near the ice edge. So these are easily detectable changes. Just need to go and record them every year. And So here's the topography. We didn't know the shape of the seafloor, so it's hard to model the circulation. So these individual dots are historical, but there's virtually no data in the fjord. So last year we had a ship go around Greenland and go up every fjord and measure all the topography for us. So here's our map of where we're doing all the temperature and salinity measurements, and the ice surveys once per year, and then we contracted out the air gravity survey for the continental shelf and all the topography of all the fjords. So we're going to have one bang-up model of Greenland at the end of 5 years. So I think I'm done. Thanks.
So we have some time for a few questions, and we have a procedure. If you have a question, raise your hand long enough for somebody with a microphone. There are 3 people with microphones. To see you, they'll bring you a microphone. When you get the microphone, please stand up. Please tell us your name, tell us whether you're a member, and ask a question. If you make a speech, I will cut you off.
We can shoot them with lasers.
Thank you.
Dale, you don't have to stand up.
Okay, thank you. I'm Dale Doucette. I'm a member. So those few of us who have sailed on the Pacific Ocean out of Seattle have run into enormous amounts of floating trash. I have looked out over the ocean and not seen any ocean, nothing but trash. So it's startling.
Question?
Now, the question is, where does most of this trash come from? Because do we track its origin, the original sources on land?
No, so most of the source of the debris you're seeing in the ocean is land, runoff from rivers and beaches and so on. But we're not very good as a society of identifying point source pollution, where they come from, in either, where pollutants come from in our sewage treatment systems, or where the trash comes that gets into rivers, all that. So there is no clear answer to that.
Does Ken have you have a?
Yes. My question has to do with calibration and validation of your sea level rise.
Mm-hmm.
Using tidal gauges in tectonically stable
Robin.
areas, it seems that the database indicates that the sea level rise is about 1/2 of what you have, 3 millimeters per year. How do you calibrate the altimeter satellite readings with tidal gauges?
Yeah. So there are actually 2 mechanisms. We have 3 highly instrumented sites offshore one in Bass Strait in Australia, one off the California coast at the Harvest oil platform, and one in the Mediterranean, which really, they're right under the tracks of the altimeter, so we can do direct comparisons. And they have millimeter per year, or millimeter level accuracies. So they're the prime, they really lock it down. And then we have 50 high quality tide gauges all connected to the global positioning system on islands around the world. Many of the 300 or so long tide gauge records are in the northern hemisphere. They're around continents. So if you just use a blank level, all the tide gauges, you are going to get a different number because they're all concentrated in the northern hemisphere. A lot of the oceans in the southern hemisphere. So we have to make adjustments and pick and choose the tide gauges that are an accurate set to compare globally.
Stuart Reuter, a member. As a retired submarine officer, I've got a question as somebody else who's touched a few salinity molecules. Every form of transportation from a rowboat to nuclear submarine puts heat into the water. is that something that we've isolated or can talk about percentages considering the number of ships out there cooling their propulsion systems with water?
It's a good question. You know, I don't want to, my instincts say that it's probably small compared to the heat coming in from the sun and the greenhouse effect, the few watts per meter squared of extra heat that goes in from the greenhouse effect. But you know, good scientists have also made interesting measurements, like how much do the fish mix the ocean compared to, you know, the wind. And there are actually some incredibly important numbers. So knowing how much our impact is, you know, from debris in the ocean and so on, it's probably a worthy endeavor to figure out how much heat that we're putting in other mechanisms. Our record of heat, the surface temperature of the ocean has been biased by the use of engine intake temperatures on ships, which read high compared to a bucket or a completely independent measurement away from a ship. So the record is mixed. You know, our climate record of temperature is mixed up with ships already.
Is there somebody else's microphone? Question.
Terry Layton, I'm a member. I'm wondering if anyone knows how much longer the oceans will continue to give us a break on climate change by absorbing heat and absorbing CO2.
Well, that's a really good question. I guess as a scientist, I'd want to know, well, what's the break? I think that we'll continue to absorb heat and CO2 for quite a while, but will the sea be worth having? It will have risen enough to get into our backyards and it won't be giving us any food anymore. So is that the break point? I don't know what the break point is, but yeah, we're fast approaching lethal levels, at least for people who live in Bangladesh or on low-lying islands in the Pacific Ocean. Maybe their break point is already had.
Question in the back.
Yes, sir. My name is Kwang Lee, not a member, first timer. Couple of questions. You mentioned the oceans is getting more acid into it. What's the #1 cause behind that? Second question, can I ask more than one question?
Mm-hmm.
Okay. Second question, we are in DC and you're an expert in this field. What would you say your best advice to the policymakers on this issue? Third question, what are the relevant technologies?
Oh, well, I didn't say three.
There's one more. What are the relevant technology, would you say, that are being discussed to solve these issues, and how plausible are they from coming into reality?
Okay, so anything that's going to capture carbon and get it out of the atmosphere is a good technology. I don't know if I really heard the first question was about the CO2 turning the acid in the ocean, and that's already causing, you know, shellfish farmers on the West Coast problem. They can only bring water into their systems part of the year.
The question was, what causes the acidification?
What causes? So carbon dioxide turns into carbonic acid when it dissolves in seawater. So we're increasing the carbonic acid level in the seawater. That's what causes the acidification. So dissolution of CO2 in seawater makes it more acid. And yeah.
No, let's have another. Oh yes, he had other questions.
Yeah. So
he basically wanted to know the policy and technological solutions to this problem.
Well, you know, I'm just an observer guy. I do not paint a target on my back by trying to pronounce policy on what society should do. I will tell you what's going on. You guys need to get out there, or the scientists I fund come and talk to people in Washington. My job is to keep the scientists alive to speak another day.
Hi, my name is Steve. I'm not a member. First time I've been to this organization. I appreciate it very much. I'm a scuba diver, and in the beginning of your presentation, you had a little bit on the reefs. Can you talk about what's going to happen to the reefs and their significance to the Earth?
Yeah, so coral reefs are like the rainforests of the sea, the greatest biodiversity in the planet, even more biodiverse than the Amazon rainforest. And we've already degraded 50% of the coral reefs on the planet. Warming is a big threat to them, and bleaching events are correlated with the high temperatures. So as long as the ocean is warming and acidifying, the coral reefs look doomed. But coral, on the flip side, corals have been around for hundreds of millions of years. They've survived asteroid impacts and all sorts of things. So we don't really fully appreciate how resilient they are. But they're resilient on a time scale that's a lot different than human time scale.
Question in the back.
Thank you very much. Divya, I'm not a member. And it was fascinating. Just wondering, the ocean floor, with all the debris going in, have there been studies to track how the ocean floor is changing, if at all? And does that even matter?
Yeah, it matters to the people who study the benthic life in the bottom of the ocean, and there's been a lot of studies recently on oil, that the oil spills, that's what sinks to the bottom, and what does it do to the ecosystem on the bottom of the ocean. But the deep sea is really hard to access and get measurements. The pressures are so high, so we don't know a lot about the deep ocean, so we could be doing enormous damage and we wouldn't be aware of it yet.
There's not a lot down there. I've seen it.
There's a lot more than you think.
I've seen thousands of pictures of the deep ocean at 2,000, 6,000 feet, and there's vast expanses of sand with a few creatures. That doesn't say anything about what kind of microbes are down there.
Yeah, the microbes are an enormous. The biggest ecosystem on the planet may live in the hydrothermal vents on the bottom of the sea.
Yes, but the hydrothermal vents are a small percentage of the land area of the ocean.
I know, but they may be the largest in biomass on the planet.
Oh, I'm not disputing that. Just saying there are vast expanses
we can
of
have an
desert
argument
down
here.
there. So I have a question for you, a technical one. If the amount of CO2 in above a body of water goes from 300 parts per million to 600 parts per million, how much will the pH of that body of water change if it starts at neutral?
I don't know. You can answer that question.
I don't know either.
Since the pH is a log function, I didn't do logs in my head since I was at MIT. But it's the small change that we've had so far in CO2 from 260 to 400. It's 140 change. It's led to a 30%.
That's parts per million.
Yeah, parts per million. Yeah. In partial pressure of CO2 in the atmosphere has led to a 30% acidification in the ocean. That's the length of the measurement bar I have.
Okay. Are there any other questions? Okay, this is going to be the last one or two. So you can go first, and then she can go.
Jim McCormick, I'm a member. What can you say about tipping points, our ability to maybe anticipate them or to watch out for them, whether it's methane melting or ocean currents changing?
Yeah, so the one tipping point that has a lot of people worried, especially a popular thing to study in Europe, is whether the meridional overturning circulation in the Atlantic would get cut off by melting a lot of the Greenland and the ice, the Arctic water, that there's fresh water at the surface, and it cuts off formation of deep water in the Atlantic, where half of the deep water in the ocean is formed in winter. And if that were to stop, then you would pull less warm water north into the Atlantic to replace the deep water formation, and that would cause a rapid change in climate. There was this movie, Day After Tomorrow, that tried to do that whole science thing that might happen over 100 years in one day, and they had the big disaster, and New York filled with ice, and everybody was getting saved and all that. But the scenario is still there, that there may be a tipping point in the Atlantic.
Last question.
That actually was my question about the North Atlantic conveyor. How much is your new information?
Stand up, tell us your name.
I forget. Elisa Wynn, guest of a member. How much is your new information that's coming in about Greenland and your new modeling and that going to affect thoughts about the North Atlantic conveyor?
Yeah, so I'm in two minds. I think that it's really important to know the freshwater input from Greenland and how much ice is melting up there. Personally, I'm not thinking that the North Atlantic circulation is going to have a catastrophic change, because most of the circulation that's going on there, the Gulf Stream and so on, is wind-driven. And I don't think that the winds in the Northern Hemisphere are going to change fast enough to cause a critical change in the circulation. But, and there hasn't been any long-term change detected in the 15 years of measurements at 26 North. We have an array measuring the whole North Atlantic overturning circulation. It hasn't changed.
Okay, I think, all right, one more right there. Last one.
I just have
Stand
a question.
up, tell us your name, please.
Hi, my name is Mary. Not
Are you a member?
I have a question regarding, I guess, the saturation of where research. Okay, thank you. The saturation of where research is conducted, and I understand completely why we need to look at the polar regions, and how that affects the study of the ocean currents. I'm originally from the Louisiana Gulf Coast, and you have municipalities down there which they have completely stopped municipal recycling pickups due to budget cuts, the economy, these sorts of issues. But these are the very same communities that are highly affected by the garbage in the ocean and the rise in the temperatures. And to be quite honest, if you tell somebody about the polar bears or a faraway place like Kiribati or Bangladesh that somebody can't find on the globe, there's this disconnect. And so I'm wondering about the saturation of research in the areas, at least in this country, versus faraway global areas.
Yeah, so I don't think you should get the impression from a NASA guy that that oceanography research is ignoring places locally. It's just that our sort of prime directive is studying the whole globe. So I try and take the big picture. But there's been a big infusion, for example, of research money into the Gulf with the Deepwater Horizon spill, $10 billion. And, there's researching every possible thing that can go on in the Gulf of Mexico these days. That's just represented better by somebody else besides me.
Well, let's thank our speaker.
Thank you.
So before you go, in appreciation for your lecture, I have a couple of small gifts to give you. One is a framed copy of the announcement of your lecture, and the other is a reprint of the first volume of the Philosophical Society of Washington.
Thank you very much. Thank you, everybody, for your attention. I really appreciate the great questions, too.
You just sit down for a few minutes.
Sure.
So before we go, we're not done yet. There are a few housekeeping announcements. First and foremost, I want to thank all our members and our guests and sponsors and supporters for coming and for supporting PSW. PSW depends on enthusiastic, active, and capable members and supporters, and on our sponsors. And without them, PSW wouldn't be able to continue to offer these lectures, and it wouldn't grow. So please join if you're not a member, and if you are, get involved in helping carry out PSW activities. You can apply for membership on the PSW website. It's really quite easy. You just get to the home page and go to membership, believe it or not. And when you go there, you'll get an application for membership. You fill it out and get down to the bottom. It'll tell you what the dues payment is. And right now it's $37.50, believe it or not, for half a year. Hit the submit button, and you'll get to the dread PayPal page. Why is it the dread PayPal page? Because everywhere you look, it says PayPal, 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 PayPal. But you don't have to use PayPal to pay your dues. you go to the Continue button just above the logos of your favorite credit cards and hit Continue, and you'll get a standard payment page, and you can pay with your credit card. So many people get hung up on this page, and they think they have to use PayPal. You don't have to use PayPal. Why is PayPal involved? Because PayPal offers a very nice fee for processing these payments. They serve as our merchant bank, and they give nonprofits a big break. And you can do this right away because Corresponding Secretary Robin Taylor and Membership Chair James Heelan are both here and will be happy to help you sign up for membership if you like. Let's see. Our next lecture. Oh, keep in mind that PSW is a tax-exempt organization, at least for now, under Section 501c3 of the Internal Revenue Code. That was not a reference to us changing. It's a reference to the tax code possibly changing. But for now, your contributions are tax deductible. Our next lecture, number 2378, will be on April 28th, 2017, 3 weeks from today. It will be right here in the Powell Auditorium. The speaker will be Anthony James, professor, mosquito expert, and molecular biologist at UC Irvine. He will be speaking on mosquitoes, synthetic biology, CRISPR, gene drive, and malaria. That is, on the use of recently developed techniques for genetic modification to control disease transmission by biting insects. We hope to see you then for what promises to be a very informative lecture. The rest of the spring schedule is as follows. After Anthony James, we have the Henry Lecture. It will be the 86th Joseph Henry Lecture. It will be on May 12th. It will be the 2,379th meeting. This year we'll be having a series of lectures on exoplanets, particularly potentially habitable ones, with a dual focus on the TRAPPIST system and on broad cosmological considerations informing us about Earth-like planets in the universe. The speakers will be Mark Clampin, Deputy Director, Sciences and Exploration Directorate at NASA Goddard, Deborah Fisher, Professor of Astronomy and Geology and Geophysics at Yale, Sean Donegal-Goldman, a scientist in the Sciences and Exploration Directorate at NASA, Aki Roberge, an astrophysicist at NASA Goddard, and Hannah Ruth Wakeford, a fellow also at NASA Goddard. We'll be posting more complete information to the website this coming week. Right, Mark? And we urge you to check the website regularly for updates to the schedule. The social hour ends at 10:30, after which PSW members and guests meet at the Fairfax Hotel Lounge, just across Massachusetts Avenue. If you want to join us, please speak with Corresponding Secretary Robert Taylor. I would say Vice President Lloyd Mitchell, but he's not here. Or perhaps Membership Chairman James Heelan. And they will escort you or show you how to get there. And please use the side entrances to exit the building. And I will now accept a motion for adjournment of the 2,377th meeting of the Society to the social hour. A second? All in favor? All opposed? Meeting is adjourned to the social hour.